Hello, my name is Daniel Russo, and this is problem number 2 from homework number 5 for EL 6303. Now, the problem gives us f of x, y, function 2 variables, 1 over ax squared, y, x is valid, from 1 to infinity, 1 over x is less than y is less than x for the boundaries of y. So the first part asks us to draw the non-zero definition region of fxy. Let's reposition my lamp here. Better light the Okay, so let's see here that let's draw this out. Now we know that x is greater than 1. So right here, when x is 1, it's going to be a boundary line. So everything beyond this line will be valid. And we also know that y is valid from 1 over x and to x. So when y is equal to x, we have the classical y equals x line. And that's the upper limit. So everything below that will be so, and then 1 over x is 1 over x is a decreasing slope function that also intersects at 1, 1. So that goes to 0 slowly. So now we have our overlapping functions with y equals x on top. This is our dz. So y equals x on top. Y equals 1 over x on the bottom. And x is equal to 1 as another boundary. So this is our non-zero definition region. So part 2, it asks us to find a so that fxy is a valid joint density function. So we know that the derivative of the joint density function is supposed to be equal to 1. So we can draw double integral 1ax squared y with respect to y and x will be equal to 1, so we want. So our limits of integration will, for x on the outside, it's going to be from 1 to infinity. We can see it 1 to infinity, ever increasing. And for y, on one side we have 1 over x as our lowest values of y, and y equals x on the other. So technically, it kind of goes from y to y in a way, but in terms of x, we can do that to help us along in our math. So we'll get x to 1 over x. So it's from y to y in a way, but from the lower limits of y to the upper limits of y for dy. So in a way you could say it's from never actually approaching 0, but 0 to y over x is sort of an answer, but you don't have those values here, so you have to use the curve as your limit. So let's start by evaluating the inside and pull everything out that's not dy, and we're left with still the integral of 1 over ax squared, x, 1 over x, 1 over y, dy, dx. And then we can do that math there. And we get the log of y, or the natural log, ln of y is from x is the derivative of 1 over y to 1 over x dx, which is further equal to 1 over ax squared multiplied by ln of x minus ln of 1 over x dx. So we can bring that over there. 1 over a, bring that out even further, by the way, infinity to 1 of, you can multiply it into there as, so ln of x over x squared minus ln of 1 over x squared dx. And this is equal to 1 over a multiplied by a little bit more space for this actually. Which is equal to 1 over a multiplied by, actually I'll do the integration under here to show this. So we're still integrating. We're not integrating actually, we've integrated ln of 1 over x minus 2 over x. So in the derivative now, and that's going to be evaluated from infinity to 1. So we're going to suss that all out down here. 1 over infinity minus 2 over infinity minus ln of infinity over infinity minus the ln of 1 over 1 minus 2 over 1 subtracted by ln of 1 over 1. And a couple of things cancel out here. These are both going to be go to 0, and we're left with 1 over a is equal to negative ln of 1 minus 2 over 1. Let's multiply inside. This will also go to 0. So ln of 1 is 0. So you're left with negative 2 over a times negative 2 times negative is just 2 over 1. And this is equal to 1. So we have 2 over a is equal to 1. So a equals 2. So now we know what a is equal to. But you might have missed that last step because I might have stepped out of the bounds there, my page. But what you missed was that this is our summing in our integration terms, and then solving. A lot of things go to 0, and then a is equal to 2. So now we can move on to part 3, which asks us to find and draw the marginal density functions of fx and fy. Now we're given, we know that fx x is equal to integration from negative infinity to infinity fx y xy dy. So for the f of x, we know that that's infinity, negative infinity, 1 over 2x squared y dy. And the limits of integration will actually be the upper limits for y, so we're dy. So those limits of x in terms of y, and we know limit of y is 1 to infinity. So the outside limits of that. So x and 1 over x, or 1 over 2x squared, y dy. And our limits have to make sense for us to get rid of the y and make it an x as well. So that's an extra added check in a way. So we'll continue further down here, pull out the 2x squared and integrate x, 1 over x of 1 over y dy. You might have noticed this looks very similar to before, so that helps a little bit too. So ln y by x, 1 over x is equal to 1 over 2x squared multiplied by ln of x minus ln of 1 over x. So that equals ln of x over 2x squared minus ln of 1 over x over 2x squared. And if you graph this, and I have in a TI-9, you will find that it is a function that starts at 1. Well, we started at 1 because it actually continues down further, but we don't care about that because that's not beyond the bounds of the problem, and it peaks up to about 1.3 and then tapers off. And that's good because it's a decreasing function. You don't want an increasing function for our probability marginal density function, similar to the probability density function and its requirements. So now we have to find the second part, the continued. So now we define y, and f of y is equal to infinity to negative infinity fx y xy dx. So the way I like to think about this one is your limits are going to be the most important aspect of this setup for this problem. So let's just start similar to before, subbing in our information dx. So we're going to want to get x out of the way in terms of y in terms of x. And we're going to have two separate areas to integrate as well, because the x has x equals 1. So to draw an illustrative graph, we're going to split our y section from between 0 and 1 and 1 and infinity. Sort of, well, not really 1 and infinity, it's more of 1 and y equals x. So y equals x, y equals 1 over x. So when y is from 0 less than y less than 1, and from 1 less than y less than infinity. And because we need to kind of get everything in terms of x, we're going to be thinking of 0 in this case as x equals 1 over y. It's the lowest value of y you're going to get. And the y, kind of think about this being turned like that, you're going to have an ever increasing x, so this will be going to infinity actually. Similarly here, this x value is going to be increasing exponentially, so x is kind of equal to infinity, and in this case x is equal to y is it's the lower limit in a sense. Because here y equals x is how it follows. This is x is equal to an ever-increasing, the y is an ever-increasing number. And similarly, you have that y equals 1 over x, so x is equal to 1 over y to an infinity. So for 0 is less than y is less than 1, this is going to be a two-part marginal density function. So 1 over y to infinity of our function, which we know, 1 over 2x squared y dx. So now we have y here. That's going to get rid of those x's. It's getting rid of those x's, which is what we're trying to do, essentially. So pull out our x squared there. Sorry, pull our x or 1 over y. And we can do the integration, which will be negative 1 over 2x. 1 to 1 over y. For infinity, sorry. And that over y is equal to negative 1 over 2 times 1 minus negative 1 over 2 times 1 over y. And you can see that sorry, it's infinity, getting a little mixed up. So this will go to 0, and we'll have 1 over y multiplied by 1 over 2 over y, which makes the y come up here, and we'll cancel those. So it's actually equal to 1/2. So it's just a pretty simple thing now. We start to actually draw it now, so we know where we are. So at 1/2, between 0 and 1, going to have a line. So now our 1 is less than y is less than infinity. We're going to have our upper limit actually be infinity, the ever-increasing y, from y to ever-increasing y. Similarly, take 2x squared out. No, sorry, take the 1 over y out, leave 1 over 2x squared dx. Similar process. One over y multiplied by 1 over 2 times infinity minus negative 1 over 2y. Well, that goes to 0. Those negatives cancel, and we're left with 1 over y multiplied by 1 over 2y, leaving us with 1 over 2y squared, which luckily is a decreasing function, which is a good check to know if this seems correct, because at 1 it's just equal to 1/2. So no discontinuity or anything weird like that. That'll be a decreasing function. So now that's our end for part 3, and the last section, question 4 asks, we found and drew the marginal density functions, but now we have to verify them, and to verify that they're valid, we have to integrate each of those density functions and make sure that they equal 1 underneath. So as a reminder, for x, we have to integrate this from 1 to infinity and find if it is accurate. It should be 1, so 1 is equal to integration from 0 to 1 ln of x over 2x squared minus ln 1 over x 2x squared dx. So this will be you can break up that actually. So I'd like to show that a little cleaner. Now we integrate on both sections there, so we have the ln x plus 1 over 2x from infinity to 1 minus negative ln 1 over x minus 1 over 2x infinity to 1. So this will become ln of infinity plus 1 over 2x minus ln 1 plus 1 over 2 times 1. Subtract negative ln 1 over infinity minus 1 over 2 times infinity. Subtract ln 1 over 1 minus 1, 2 times 1. So infinity goes 0, this is infinity, left a little x in there, divided by infinity, so you're going to get. So that leaves us with this, which is ln of 1 is 0. These are negative 2. The negative. So that leaves us with positive 1 over 2 minus 0 negative 1 negative stays negative over 2, which is equal to 1/2 plus 1/2, which is equal to 1. So that is a valid density function. Now for y, we already know 0 less than y less than 1 is equal to 1/2, so you only have to integrate with respect from 1 to infinity of 1 over 2y squared dy, which is equal to 1 over 2x. Oh, sorry, 1 over 2y from infinity to 1, which is equal to 1 over 2 times infinity minus 1 over 2 times 1. This, of course, goes to 0, and we're left with 1/2. So 1/2 and 1/2 is equal to 1, like we found earlier, and these are both valid density functions because they equal 1 when integrated underneath. So that's 1, and this is 1, and that is the end of problem number 2. Thanks for watching.